Hey guys, sorry I can't be there today, but welcome to the notes for 4.6 numerical integration. There's a bunch of learning targets listed at the top of your page, but really the only thing that I need you to know how to do are the trapezoidal and the midpoint. We're going to skip over Simpsons. It's not important for us. The trapezoidal rule and the midpoint rule, both of them have formulas that are listed inside of that section. I do not suggest that you take the time to memorize the formulas. You can look at them and you'll definitely be able to see the relationship between what we do and how they've set up those formulas. However, if you know how to calculate the area of a trapezoid and if you know how to calculate the area of a rectangle using its midpoint to determine height, you can do this without any formulas at all. In fact, it should be really, really nice and simple. I do want to point out that I have chosen two examples here for trapezoidal and midpoint approximations that both hinge on using data. That's because typically the AP loves to use data rather than functions, but the same thing could be said here for using a function as your baseline here. You can use functions to calculate Riemann sum approximations with trapezoidal approximations and with midpoint approximations. These are just two other methods. There's 6 in total. You've got upper, lower, right, and left, and now you guys will have trapezoidal and midpoint approximations. So let's talk about a trapezoidal approximation first. It can be really helpful to draw a picture, especially at the beginning here, to give you an idea of what's going on. So I do want to point out, it's asking us to take this table of data here, where our temperature is given in degrees Celsius for the water in a pond. They're going to tell you that you have a differentiable function W over time, T, and you've got a few specific values over this 15-day period. We want to approximate the average temperature in degrees Celsius of the water for the entire time frame from 0 to 15. A really common mistake is that kids just average the values and divide by how many there are. The problem with that is that the temperature of the water is always changing, not just day by day, but minute by minute, second by second. And we don't have all the data points to accomplish a true average. So what we want to use is the data that we have in the table to come up with an estimate. And anytime we're talking about estimates, we're talking about Riemann sums. So we are going to find our average temperature here using a trapezoidal approximation. They've listed for you exactly how they want you to set this up, and they're giving you the width of your intervals. So I am going to compute the average temperature. And if you remember, we had a formula, courtesy of the mean value theorem for integrals, that said you would take 1 over the length of your interval. So in this case, 15 minus 0. My interval is given to me right here. And I'm going to integrate by adding up every single temperature between 0 and 15 for my temperature function with respect to time. I'm going to use a trapezoidal approximation to come up with a value for that integrand right there for that integral. So visually what's happening, and you'll start to notice that once you do a few, you can probably do this without the graph, but you can visualize what's happening probably the best at the beginning by making a graph. So I'm just going to count off by 3s here to represent my time on the bottom and my temperature going up the y-axis. I'm not going to worry about being too particular about it. I'm just trying to give you guys an idea of what this looks like. So at time 0, I want to be at 20, and we'll count by 5s, I suppose. So 5, 10. And I'm going to go ahead and just really quickly plot all my points. So 331 is on my graph. 6 should be at about 28. And 9 at 24. So a little scatter plot of my data. And for a trapezoidal approximation, we are going to construct trapezoids. I know, creative. So my first trapezoid will be 3 units long, and I will use both endpoints. Unlike my right and my left approximations, I'm going to use both endpoints to come up with the area of that trapezoid. So off to the side here, the 1/15 is because I'm computing the average temperature of the water. Again, this has me adding up all the temperatures between 0 and 15, and I'm going to approximate the integral by using the Riemann sum. So for this particular problem, right, the area formula for a trapezoid, maybe I should put that off to the side. Area of a trapezoid is 1/2 base 1 plus base 2 times your height. In a trapezoid, the bases are your parallel sides. The height is the distance between your two bases. So on these problems, my bases are actually those coordinates that are part of my function. So I would have 1/2. The two bases would be the data points at 20 and 31. And then my height is the distance between bases. And for me in this problem, that's going to remain the same for each computation. It'll be 3. And then I would go ahead and I would construct the next trapezoid. I will be connecting, right, I'm going to have some overlap here. I'm going to be connecting with the orange here. Got an old pen. And so with that orange trapezoid, again, the formula is 1/2. Base 1 would be the height at 3. Base 2 is going to be the height at 28. And again, for this particular problem, the distance between my bases, the height of that trapezoid is 3. I'm going to kind of run out of space here, but you can start to get the idea. So what's going to happen next? I'll construct another one. That green trapezoid, I'll be adding in 1/2. The two bases are my two data points, so 28 plus 24. And again, the width or the height of that trapezoid is 3. I'm going to run out of colors here. We've got another one. I'll be adding in 1/2. The two bases would be represented by the two data points. So that would be what, 24 and 22. And then last but not least, our last trapezoid from 12 to 15. And those two data points, we're going to be adding in 1/2. We've got 22 plus 21 times 3. All right, if I look carefully, I have some common factors. The 1/15 is still a scalar hanging out on the outside, and that's because this particular function, or this particular question, asked you for the average temperature. So that's the role the 1/15 is playing. If I look at all of my computations, they all have a 1/2 in common, and they all have a 3 because these particular rectangles, whoops, I missed one of my 3's, didn't I? There should be a 3 right here. They all have a 3 because they all have equal width. So I'm going to use those as my scalar multiples. And then on the inside, I would really just have all the sums left. I'd have a 20 plus a 31, plus a 31 plus a 28. And if you look carefully, right, you're going to have that first one. But then you're also going to have a 31 here and another 31 there. So you're going to have 2 31s. And then you would have a 28 from the orange group, but you're also going to count that second 28 twice, right? Because it's got that overlapped side. So you're going to have 2 28s that you're adding together. Likewise, 2 times 24. I keep running out of space, sorry. I have 2 times 22. And then last but not least, the 21 on the edge here, right? That base only gets used one time. There's no overlap on either of the ends. So again, notice our first data point and our last data point are 21. Because they don't have overlap, there's no 2 involved. If you guys were to go and look inside your textbook and find the formula that's given for the trapezoidal sum, you'll notice some commonalities. They're going to have this 1/2. They're going to have the width of the base, and they're going to have all these 2 on the shared sides. You don't have to memorize the formula. You can just sort of know and realize what you're doing. And if you're thinking about the shape of the trapezoid, the area of the trapezoid, you should be fine. Let's see. So I end up with 1/10 on the outside. I've got 1/15 times 1/2, that's 1/30. 3 over 30 would make a 10th. And then I've got to go ahead and maybe grab a calculator, right? Probably would need a scientific at the very least. 2 times